Hello, welcome to the Master Series at Cisco Live in Barcelona. I hope everybody's having a great Cisco Live so far. And what we're going to talk about in this session, as you can see through a title, is we're going to talk about solving the big problems. We're going to ask and hopefully answer the question about what can a few talented, committed engineers accomplish. So by way of introduction, my name is Dave Zacks. I'm a Director of Innovation in the Cisco CX team. I focus on many different things inside the company, including flexible hardware, which I talked about earlier today, fabric networks, assurance, machine learning. Been with Cisco about 20 years. And I hope to have a talk today that is going to be really, really interesting for you, and maybe different than any other talk that you're going to see at Cisco Live. So what are we really tackling in this talk today? Well, what I really want to take you on is a bit of an ambitious presentation. This is a journey that we're going to go on from innovation from the lowest levels in silicon to the highest levels of solutions in networks. And we're going to try to tackle all the way that from the low level to the high level, all the way in the next 40 minutes. So let's get started. Let's start with the basics. We're going to start talking about quantum tunneling challenges at the 7 nanometer process node in silicon. So as you probably know, quantum mechanics dictates that we have whenever we have electrical fields in close proximity, that we have leakage between different areas within a semiconductor. What we're going to take a look at is the leakage. We're going to start off with the leakage between multiple gates and multiple drains within a piece of silicon. We're going to examine some of the formulas that are basic constructs in making this work, and specifically we're going to start off by taking a look at this paper, which is a design of 14 nanometer tri-gate transistors on bulk wafer FinFETs. So let's get started. Now, you actually think I'm going to talk about that, don't you? I'm not going to talk about that. I'm actually going to talk about something totally different and something that you've probably never seen in a Cisco Live talk before, but I think I hope will be really, really interesting for you. I'm going to put up an assertion that I strongly believe in, and this assertion consists of 5 words. It's important to have heroes. I strongly believe that it's important to have heroes in your life, people that you look up to, people that embody some of the elements of what you potentially yourself would like to be. Some of my heroes would include people that you would recognize, like Albert Einstein, like Steve Jobs, like Elon Musk. These are people all embody different elements that in many ways are very admirable, and you may look up to these as heroes. And we all have our individual heroes. These are some of mine. But what I want to talk about is somebody else who's one of my heroes, somebody else that you're probably not familiar with, and that person here is this name, Paul Castenholz. So you're probably not familiar with Paul. So let me explain a little bit about Paul's background and what he did. And as I go through our presentation, I hope to explain to you why he's one of my heroes. Paul was a senior rocket engineer working at a company called Rocketdyne. So Rocketdyne, and Paul specifically at Rocketdyne, he had a long career in designing the rocket propulsion systems for various different projects. He worked on multiple engines in the Saturn program for Project Apollo that got a man to the moon. He was actually the program manager that developed the space shuttle main engine. So he had a long career in rocketry, and I'm very interested in and passionate about rocketry. So Paul is one of my heroes, and I hope to explain to you why. Now, as we take a look at what can a few talented, committed engineers accomplish, who do you think this is a picture of? And most people will look at him and say, well, I recognize that person. That's Paul Bezos. He's the CEO of Amazon. But then I'll put up this picture and say, what is that a picture of? Now, when I saw this picture in publication a few years ago, I was extremely excited when I saw this picture. But what is that a picture of? It looks like a person on the deck of a ship washing off something that looks like a big manhole cover. He's washing that off. When I looked at this, I thought, oh my goodness, look at that. That is the critical component that really got the man to the moon, because that is what's called the injector plate from an F1 engine in a Saturn V moon rocket. I was so excited when I saw this picture. Now, what's the connection between this critical component from the moon rocket, the injector plate in an F1, and Jeff Bezos? How are those two things connected? Well, Jeff Bezos actually has a company called Bezos Expeditions, and they recovered those F1 engines from the bottom of the Atlantic Ocean floor, because after, of course, the moon rocket launched, the first stage cuts off, it crashes down into the ocean and sank, and they recovered those off the ocean floor 14,000 feet down. That is, pieces of the rocket are actually visible in museums. There's a museum in Seattle that actually has these components of the rockets that you can view. So let's examine and talk a little bit about the Saturn V moon rocket. Now, as we're explaining this, I actually brought a Saturn V with me to the show today. It's right here. Let me grab it. So this is a Lego model that I built of the Saturn V. It's a complete moon rocket. It actually consists of 1,969 pieces. This was my very first Lego project that I ever built, and I built this over the holidays that have just gone by. So to explain a little bit about this rocket, it's really a 3-stage rocket. It consists of 3 individual stages. And let's take this apart so we can actually see the individual stages here. Here's the 3rd stage that I'm taking off right now. And then this is the 2nd stage. And then we have the 1st stage here. So let's examine what each one of those stages is kind of all about. So it's a 3-stage platform. It takes 3 stages to launch a man to the moon. The complete rocket, as you can see here, weighs about 6.4 million pounds fully fueled, so about 3,000 tons fully fueled. It has about 7.5 million pounds of thrust in the 1st stage. So 7.5 million pounds of thrust, 6.4 million pounds of weight, 1.1 million pounds of positive thrust, and up it goes. 7.5 million pounds of thrust comes out of 5 engines in the rocket. Then we have the 2nd stage, which also consists of 5 engines, but they're a different type of engine called the J2 engine. This is a cryogenic engine. Altogether, they develop about 1.5 million pounds of thrust. That's out of the 2nd stage here. And then finally, the 3rd stage, which is one J2 engine, and this is what actually the stage that would take the man to the moon. This component would go into orbit around the Earth. This stage would actually burn again a 2nd time to launch the person towards the moon. Then they would jettison the 3rd stage, and the lunar module and the command service modules would actually end up going to the moon. So we're going to talk a lot about the development of this rocket, specifically about the development of the engines on the bottom of the 1st stage, because that's really what my hero, Paul Castenholz, worked on and perfected the rocket engines that are in there. So this vehicle is one of the most complex machines that's ever been built by humans. It had over 3 million parts in the rocket in total and stood fully assembled over 363 feet tall. So it's just a massive, massive thing. If we had a human being standing next to this, the human being would be smaller than my fingernail here compared to the total size of this rocket, just to give you some idea of how large that actually is. And there was actually challenges between the different teams, the German team and the American team, that were working on developing this rocket in terms of doing what they called man rating the rocket stack. In other words, how many times do we build this rocket in total before we dare to put a person on top and actually launch it? That's called man rating the rocket. Now, if you take a look at what the commitment that the United States made of getting man to the moon, you had John Kennedy, who stood up and said, this country should commit itself before the decade is out to the goal of landing a man on the moon and returning him safely to the Earth. In other words, this is a goal, landing a man on the moon and returning him safely to the Earth, and this is the goalpost before the decade is out. So in order to actually get to the stage where they could be prepared to launch this complete, very, very complex vehicle to the moon, there's 2 approaches to engineering that. One would be to build and test the 1st stage multiple times. Then once you've got that perfected, to build and test the 2nd stage multiple times. And then once you've got that perfected, to build and test the 3rd stage multiple times. And if you had unlimited time, you could do that. But we have to get a man on the moon by the end of the decade. So that was just several years to get it all done, to build and assemble this massive rocket. So they moved to a system called all-up testing. All-up testing basically says they built the entire rocket stack all at once, all that complexity, and launched it all at the same time, right? So this was the concept of all-up testing, which was really the brainchild of a gentleman named George Mueller, who pushed this concept through to considerable resistance, I might add, initially inside the organization. But eventually they had to move to all-up testing to meet this timeline, to meet this goal. So you can imagine the pressure that was on the engineers to achieve such a complex thing in such a short amount of time. Now the F1 engine on the bottom of the rocket in particular was revolutionary, much more revolutionarily bigger than any other engine that had ever been built before. Here's a picture of Werner von Braun, who was the father of the Saturn V, the inventor of Saturn V in many ways, next to a picture of just one of the F1 engines. And you could just see the massive scale of that F1 engine here compared to a human being. They're just massively huge. Now we're going to talk a lot about the engineering of the F1 engine, but what I'd really like to do is kind of let the engine speak for itself for just a minute or so and let you observe the awesome power of this engine during a liftoff. So let's take a look at that. Actually being sucked down into the vacuum of the engine as it creates it during launch. Just astounding to see the power of these engines. I never get tired of watching these videos. So the F1 engine was the instrumental component that was used for the first stage engine in the moon launch, the engines on the bottom of the first stage. And what did this first stage actually do during launch? Well, it launched the entire rocket stack, remember 6.4 million pounds of rocket, 50 miles downrange, 40 miles in altitude, accelerated the rocket up to Mach 7, 7 times the speed of sound. It only lasted for 2.5 minutes during flight before they would cut off the first stage and go to the second stage. And during that 2.5 minutes, it would burn 4.5 million pounds of fuel. So it's just kind of astounding that this engine that they created was much bigger than any previous engine. It was on the order of 10x bigger than any engine that had been successfully built before. And it was a massive, massive engineering problem to build something that big. In rocketry, when you increase the power on a rocket by 10 to 20%, you've achieved something fairly significant. Here they were going, 500 to 1,000% bigger than the rocket engines that had previously been built. And that's what you have to do in order to get to the moon. It's just math. You work backwards and say, the space capsule weighs this much, the lander weighs this much, and you just do the math and work backwards, and you find out that the rocket, to get to a moon, has to weigh on an order of 6 to 7 million pounds. So it's just a massive, massive structure. So here's a close-up view of a little bit of the F1 engine. I'll just point out a few key components to it here. 1.5 million pounds thrust per engine. This is the biggest liquid-fueled rocket engine, even to date, that's ever been built. It had a chamber pressure approaching 1,000 psi inside, 1,000 pounds per square inch, and a temperature inside the combustion chamber approaching 6,000 degrees. So imagine the materials that you have to build this out of to withstand that kind of temperature and pressure. So let's zoom up a little bit on the top of that engine. This is a picture I actually took of the back of one of those engines when I was visiting this at Cape Canaveral at Kennedy Space Center. And one of the things I've circled there, if you can see it, it might be a little bit hard to see, but right in the center here, you can see this component, which is, if you recognize it, is that plate, the injector plate that person was washing off on the deck of the ship before. That's what sits right at the top of the engine bell, and the injector plate is where the fuel comes together, what we call RP1 and LOX. RP1 is rocket propellant 1. It's basically a highly refined form of kerosene, and liquid oxygen come together at the injector plate, mix and combust and burn. So the fuel rates through that engine are pretty astounding. 24,000 gallons of liquid oxygen and 15,000 gallons of RP1 per minute per engine. That type of flow rate, by the time we have 5 engines on the bottom of the Saturn V, will empty an Olympic-sized swimming pool full of fuel within about 3 minutes. So it's just an astounding amount of fuel that has to flow through these injector plates. Now the big problem they had when they developed this engine is it's what we call dynamically unstable. So let me explain a little bit about what that means. When the engine is burning and the fuel is combusting, there are pressure waves that form within the engine bell. This is normal and natural, but the engine waves need to dampen themselves out. The pressure waves basically need to dampen out in there so that we don't get our self-reinforcing construct going, where basically if the pressure waves start to feed on themselves, the engine within a couple of seconds will either melt or explode. And if that's happening below 6 million pounds of highly volatile rocket fuel, it would instantly be adios rocket, adios astronauts, and because that would be happening live on national TV, adios moon program. So it's very, very important to solve this problem of the instability of these engines. Now, what they do when they're testing engines is they put them onto a test stand out in the desert, and they test to see how well does a rocket work. Do we burn it for a few seconds, and a few seconds more, and a few seconds more, up until the full rated thrust of the engine. And in June 28th, 1962, combustion instability resulted in a total loss of one of these F1 engines. So what that means is, when they were putting it on a test stand like this, you can see the big fuel tanks up top, and you can see the engine burning at the bottom, just like we saw in the video, that engine burning, they're burning the engine on the bottom there. One of these engines basically exploded on the test stand, totally destroyed the test stand, fuel everywhere, rocket components everywhere, and if that had happened for real during a launch, it would have been a total loss of the rocket. So as von Braun dryly remarked at that point, this problem of combustion instability assumed new proportions, right? It's taking a gentle stab at it, I suppose. So this problem really got handed to a team led by 3 people to fix. Jerry Thompson from NASA, my hero Paul Castenholz, and Dan Clute from Rocketdyne, the company that was actually building the rockets. They have to diagnose the problem, come up with a solution, and test the F1 unit until they can actually certify it as flight ready. Now, this combustion process is too complex to be simulated on a computer. They basically have to resort to seat-of-the-pants engineering, throwing all their skill and all their focus at solving this problem. And what's at stake here? If they can't fix this engine, nothing else matters. The entire moon program rests on getting these engines on the bottom of the Saturn V to work, and to work reliably. In other words, this is a situation, right? They have to solve the problem. This is a complication. It's too complex to simulate, and this is the implication of what's at stake if they can't fix this problem. Now let's zoom in a little bit more on that. This problem actually took over 24 months to solve, over 2 years to perfect this engine. But this wasn't just happening in isolation. If we take a look at the timeline here, up to and through the moon landings, this was a timeline when they were working on testing and perfecting, if they could perfect it, the F1 engine. About that 2-year period. But all of Project Apollo was going on at the same time. Now, I've adjusted the costs here of Project Apollo into today's dollars, and you can see through this graph that at the peak of Project Apollo, it was over $40 billion a year that the moon program was being expended on the moon program. Over $200 billion in total in terms of adjusted dollars. And if they can't get the F1 engine working during this period here, this 2-year period where they have to basically solve all the problems with it, then none of the rest of this is going to be possible. There aren't going to be any moon landings. There isn't going to be a space race. There won't be Skylab. There won't be all the things that came out of the Apollo program. And you also have to remember, this wasn't happening in isolation. All the rest of the Apollo program was going on at the same time. The people developing the second stage and the third stage and the lander and the Apollo spacecraft, the command service module, all that being developed at the same time. The ground support facilities, everything else, all the subcontractors. There were over 400,000 people working on Project Apollo at the peak. But if these 3 people leading this team can't solve this problem, there's not going to be any moon landing. So imagine the pressure on these engineers to solve this problem. Now, this also didn't happen in isolation. It got out into the press that there were problems with the development of the moon rocket. This was public. It wasn't just happening in private. It was happening very publicly that they had a problem in developing these large rocket engines and getting them to work and to work reliably. So it turned out it was actually useless to try to design the F1 engine so it never went unstable. The engine was too big. There were too many complications. It was subject to too many disturbances inside the engine. They could never dampen out the instabilities entirely. What they needed to do was to move to a concept called dynamic stability, which meant that once the instability started to happen, the engine would automatically correct itself, and they needed to do that within a maximum of 400 milliseconds. So once a disturbance started to happen, it would dampen itself out within 400 milliseconds. Now, they actually developed a component inside the engine called the rough combustion cutoff that if the combustion became unstable for longer than that, the engine would automatically shut down so they wouldn't keep destroying engines during their testing. However, the problem is that doesn't work for a real launch, because if you're launching the rocket and the engine cuts off, you don't have enough thrust to get into orbit. So they really have to solve this problem of combustion instability. Now, the key to this was the injector plate. Remember that piece that the person was washing off with the hose on top of the deck of the ship? That's why when I saw this picture, I was so excited about this injector plate, seeing it for real and seeing it recovered from the bottom of the ocean, because this was the key, the heart of the system. Now, if you look at that injector plate, you'll see hundreds and hundreds of holes. There's about 3,700 holes on it in different patterns, in different places. And then there's these big copper baffles that are around it. Those holes are how all the liquid fuel, both the RP1 and the liquid oxygen, are vaporized and injected into the engine bell. And it turns out the placement of the holes, the pattern of the holes, and the placement and pattern of the baffles has everything to do with the shape of the flame that burns at the bottom of a rocket engine, and has everything to do with controlling or not controlling the combustion instability problem. So the engineers initially installed a series of copper baffles. I've highlighted some of them here so you can see them. And these help to control part of the problem. They basically had problems developing these too, because the initial ones they put in were too small. They warped under the pressure of a massive flame that the engine would burn with. And so a few quotes here from Jerry Thompson. We tried every trick we could think of. It got so the engineers couldn't come up with a theory for the plate that they hadn't tried before. So they had to keep iterating and iterating and iterating at this problem. And one of the big challenges they had is that the combustion instability was both intermittent and unpredictable. Does that sound familiar to anybody who's dealt with networks before? Intermittent, unpredictable problems? I think as network engineers, we can kind of empathize with that. There was no consistency. The combustion instability would happen for reasons that the engineers never really quite understood. So they had to keep iterating and iterating on solving this problem without necessarily having a great definition of what the problem was. Now, they had to eventually got to a point where the engine would no longer become dynamically unstable. But that wasn't good enough for these engineers. They decided that they had to introduce instability into the engine. In other words, they wanted to be able to produce instability on command. So what they would do is they got to develop a test where they would actually initiate instability by putting a black powder charge, basically a bomb, inside the engine bell and set that off while the engine is firing. In other words, when you have the engine firing on the test stand like this, they would set off a bomb inside the engine that would cause a massive momentary overpressure, and the engine had to survive that too. Obviously that could never happen for real in flight, but they needed to introduce instability, the worst possible instability, and then the engine had to dampen this out as well. So really it became about testing and iterating and testing and iterating, small refinements, small steps forward to move towards their goal. And in mid-1964, they actually came to a conclusion of changing the angles of the holes within the injector plate. This actually reduced the efficiency of the engine a little bit, but it markedly improved combustion stability. So more and more adjustments were made till eventually they could set off a bomb inside the engine bell while the engine was firing, and the engine would dampen out that instability, not in 400 milliseconds, but in 100 milliseconds. So this was a major, major achievement in terms of making this engine stable enough to launch people on. And this really, for Rocketdyne, was the turning point. So if we take a look at this graph here shows the cumulative burn time on the F1 engine. You can see how it starts off with not very much burn time in 1962 and 1963, and they're getting more and more time burning and testing the engine. That 2-year period, 2-year plus period we talked about before, was broken into about 7 months of testing with low thrust and about 11 months of testing with rated thrust, with full rated thrust, so about 18 months of testing, during which they would test and refine for that spontaneous combustion problem, spontaneous instability problem. And then about 9 months more of testing with forced instability, that's setting off the bomb inside the engine bell. So by the time they got to the end of this, they had a very smooth running engine that would work smoothly under almost any conditions. And you can see from there, they got more and more and more testing, more and more burn time into the engines to a point where they were ready to actually do the first flight the first full flight. Remember, we talked about all-up testing, because this is just the first stage, but they were also testing the second stage, the third stage, all-up testing, first flight of the Apollo Saturn V moon rocket. The first crew was put on the rocket here in late 1968 with Apollo 8, and they orbited the moon. Apollo 11 launched in July 1969, landed on the moon on July 20th, and then all of the follow-on missions, and even beyond Apollo, including into Skylab. If we take a look at the what was achieved here, Rocketdyne will say that one of the stiffest challenges the company ever faced was their combustion stability investigations, and solving those was one of their most satisfying achievements. All rocket engines have this concept to some level of combustion instability, but the huge size of these engines dramatically increase the size of the challenge in terms of solving it. And that injector plate was really key to solving it. That's why I make the assertion that this was the key component that got a man to the moon. Now here's the result. The Saturn V is one of the most successful launch vehicles that was ever launched, never suffered a catastrophic failure of the F1s. And look at that rocket in flight. Remember I said the rocket itself is 363 feet tall, but the flame coming out of the back of those engines is a third of a mile long. It's just incredible, the power and the capability of these engines, and it was really an engineering triumph to create these. So that's why I got so excited when I saw this picture of a person sitting on the deck of a ship washing off that component, washing off the injector plate, because to me, this is the central component that put a person on the moon, and just an incredible feat of engineering. And remember, this really came down to only a few people to solve this out of 400,000 working on Project Apollo. So how is this related to what you, as a network engineer, do every day? I mean, I really like rocketry. I hope you can sense some of my passion about rockets and high-performance aircraft and this kind of thing. I'm very, very passionate, very interested in those things. But how is this related to what we all do every day as network engineers? Well, we're not building a rocket with 3 million pieces in it. We're not building a rocket with 3 million parts, but we do build networks that have thousands of devices, tens of thousands of users, hundreds of applications, quality of service, embedded security, all the different functionality, multi-pathing, failover, redundancy, all the different complexity that goes into building a network. And I would argue that effectively what we're building with networks is a huge distributed machine. Just like building, the complexity of a rocket, we're building the complexity of the massive networks that we all work on. So in my opinion, it's very comparable. And also, just like the moon landings depended on this rocket, your company absolutely depends on the network. Think about what happens in an organization if you take the network away. If you were to say, okay, I've got a major, let's say, hospital, and the network simply goes down, goes away, that's probably pretty catastrophic to the proper functioning of that organization. So companies that you deal with, no matter what industry you're in, manufacturing, healthcare, retail, everybody depends on the networks that we all build, that you build. And as a network engineer, you get to design the solutions. You get to solve the big problems. In other words, you get to be the hero, just like my hero, Paul Castenholz. So I think it's critically important to understand the level of importance and the level of criticality to what we all do in building these large, complex, distributed networks. You should be proud that you get to be the person that actually gets to step into the breach and solve these big, important problems when they arise and design the solutions and the next generation solutions. It's an incredible privilege, and you're carrying on an incredible heritage of the engineers that have gone before you that maybe worked in a different discipline like rocketry, but really there are many, many things that are comparable between what a rocket engineer would work on and what a network engineer would work on. So like I say, this is one of the reasons why Paul Castenholz is one of my heroes, because he was central to leading this team that solved the problem with the F1 engines on a Saturn V. So if we take a look briefly at what does the future hold, in my opinion, we're living in another golden age right now of space exploration. Just like the 1960s was a golden age with Apollo, we're really living in a golden age in many ways. Most people probably know there's a mission underway inside NASA called Artemis 3. The Artemis 3 mission is designed to put people back on the moon by 2024. This is the current goal. And that will actually launch on a new rocket that NASA is building called Space Launch System. This will actually also dock in orbit around the moon with a new space station that will be built that won't orbit the Earth, it won't be in lunar orbit, it will orbit the moon. This space station will be called Lunar Gateway, and it's actually what the astronauts will dock with, work there before they go down to the moon surface and after they come back up. So we'll actually have a space station, not just in orbit around the Earth, International Space Station, but in orbit around the moon as well with Lunar Gateway. Now, here's a few more details on the Space Launch System that NASA is putting together. This is actually going to be built in several stages. The first stage will be Block 1, which can send 26 metric tons into orbit. This will be twin 5-segment rocket, solid rocket boosters on the side, very similar to ones with the space shuttle, but more powerful. And they'll actually be reusing the main space shuttle main engines that my hero Paul Kastenholz was program manager on the RS-25s. They will be reusing those on the core stage as well. And by the way, the core stage of this just rolled out of the Michoud assembly plant last month, so they are making good progress now on putting SLS together. This will be enhanced in future with a Block 1B exploration upper stage, which will actually have the power to get humans to the moon and to get humans potentially farther out into deep space as well. It can launch a bigger payload. And then beyond that, we'll go to Block 2 of SLS, which actually have a total, amazingly, of 11.9 million pounds of total thrust. If you compare that to Saturn V, biggest rocket that's ever launched before that was 7.5 million pounds. Now we're going to be on almost 12 million pounds of thrust, and this would give us the ability to lift up to 45 tons of payload out into deep space. So this will be a pretty amazing rocket when it launches, and it's currently slated to launch for the first time with Block 1 next year. Now beyond that, of course, there's also a lot of other things happening in rocketry. We have SpaceX, who's been developing amazing rockets, starting with the Falcon 1 in 2008, which was SpaceX's first rocket they launched into orbit. And that was designed to carry the Dragon capsule. The Dragon capsule, carried by Falcon 1 and now by Falcon 9, is what is actually designed as an uncrewed component that is designed to do things like resupplying the International Space Station, for example. Now, to actually launch the Dragon rocket, this is one of the reasons they had to move from Falcon 1, the initial experimental rocket, up to Falcon 9 to carry their heavy payload of this. Now, one of the things that was just tested recently, about a week ago, was Crew Dragon. So Crew Dragon is the module that will actually allow humans to be launched on top of a Falcon 9 rocket and carry humans back in orbit from US soil back to the US, to the International Space Station, carry US astronauts there. Now, this just went through a test where NASA actually blew up a Falcon 9 rocket. They launched it, exploded the rocket deliberately partway through flight, and you tested the crew escape system, those rockets on the side that are called Super Draco rockets that launched this capsule off the top, and basically that would be used for the astronauts to escape if there was a real emergency during the launch. So that was really the last big test that they have to go through with the Crew Dragon before launching it for real up into space. Now, beyond this, of course, the next stage is going to the rocket which was first tested last year, which is Falcon Heavy. Falcon Heavy is very interesting. It's actually a 3-core rocket, 2 outer cores and an inner core. And of course, the real innovation that SpaceX has brought into the market is the concept of reusability. I don't know if you got a chance to watch the first Falcon 9 launch, the first Falcon Heavy launch when it launched, but it was an absolutely amazing launch. They used clustering technology with the rockets on the bottom, so it has a total of 27 rocket engines that Falcon Heavy launches on, 9 in each one of the 3 cores. And it was just amazing to watch that not only this rocket launch, but to have the 2 cores come back and land in synchronization. It was beautiful. It was almost like ballet, watching the 2 rocket cores land after propelling the main core out into space. It was incredible to watch. So this concept of reusability is really the key component that SpaceX has brought. Now, in addition, of course, they're working on other rockets beyond this, like Starship, for example. So Starship will be an even heavier lift rocket, and this is really part of Elon Musk's plan to take human beings well beyond Earth orbit and out, in fact, to Mars, and to create ultimately a self-sustaining colony on Mars. is incredible work that's being done by SpaceX and other private space contractors. I wish I had time to talk about everybody that's doing things in space these days, because there's many, many companies working in this area, but SpaceX is doing some pretty amazing things. So we've seen these heavy lift rockets like Saturn V. There's other ones. A lot of people don't know that the Soviet Union was actually developing a competitor to Saturn V to get a man to the moon, called the N1 moon rocket, of a comparable size and scale. The Energia rocket, also developed by Russia, and Falcon Heavy, which we talked about, and also boosters that come from elsewhere. Like, for example, the Chinese have boosters, like the Yenisei rocket, the Long March 9, which is currently under development, hasn't launched yet. And as I mentioned, things like SLS, Block 2, and Starship. These are all different heavy lift rockets that are being under development right now. Now, and I think these are, in many ways, are very comparable to the heavy lift networks that we all build. SD access, SD-WAN, data centers, all of these massive networks that we build, in my opinion, are very comparable in many ways in terms of the complexity and the mission criticality to the rockets that we are examining here and designing and building. So let me wrap up and conclude with where I started with. I think it's very important in your life to have heroes, people that you look up to, that embody some of the things that you want to be. And maybe that's one of those heroes is who you already are. I pretty much can state that a lot of people are already heroes in somebody else's life. So you may already be a hero. That might be to people in your family, it might be people that are your coworkers, but it's very, very important for you to be a hero to them. But it's also important to have heroes, because heroes are who you can aspire to be. So when I think about somebody like one of my heroes, Paul Castenholz, I think about the qualities that he embodied. I think about the capabilities and the things that he accomplished, and it's absolutely phenomenal. It's very inspirational for me to have people like that to look up to, and I think that you can think about this in your own life and think about many, many different places where you have heroes, or you can think about people that are heroes to you in different ways. So I'm going to conclude and wrap up with this. This is something that's written on a wall in Vancouver. It's a wall mural on a building out in Main and 7th in Vancouver. I've always loved this saying: you never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it is the only thing that ever has. I think that's just a great saying, but I'm actually just going to change it a little bit, and I'm going to replace that with a small group of thoughtful, committed engineers can really change the world. And think about the people that worked on Project Apollo. These engineers changed the world. They changed our perception of what possible is. They changed it from it's impossible to put a person on the moon to of course we can put a person on the moon, and we have that technology and that capability and that power. So this is just something you should be very proud of as an engineer, is that you have the ability to contribute in a way that materially impacts and changes the world. Now, I'll finally wrap up by saying, if you do want us to understand, where I was kind of joking at the beginning of the presentation about understanding network innovations from the bottom up, you can attend the session that I'm doing with my compatriot, Peter Jones, tomorrow here at Cisco Live, called Cisco Silicon, the Importance of Hardware in a Software-Defined World. And that's where I promise we won't go into quantum tunneling challenges at the 7-nanometer process node, but we will talk about how we develop Cisco Silicon and how that actually impacts all the products and solutions that we build. So, and like I say, I'm co-presenting that with my compatriot and friend, Peter Jones. And with that, I will wrap up and wish you well on your own personal journey, both here at Cisco Live and in your life as an engineer.